looking at our asymptotes, and also looking at points of discontinuity. So just a reminder that we have rational expressions written as a polynomial divided by a polynomial. And the first scenario we're going to look at is when we don't have any factors in common. And when that happens, we can have a vertical asymptote, and we may have a horizontal asymptote. Where do your vertical asymptotes come from? You guys remember? So the vertical line where the graph won't hit.
Your non-permissible.
Excellent. It's your non-permissible values from your denominator, and that's because you can't divide by 0. Okay, so the polynomial that's in the denominator, you don't want to have values of x that make it equal to 0, so you can't divide by 0. So whatever the values of x would be for that to equal 0, that would be your vertical asymptote. That's where the graph will not exist. And I realize you haven't done these lessons, so it might be a little today, but we'll catch you up. Okay. Then we have horizontal asymptotes, which would be going side to side. And those come from 3 different rules. The first rule we looked at was when the degree of the numerator is less than the degree of the denominator. So let's say, for example, if we had x plus 2 divided by x cubed minus 1. Okay, the degree of the numerator is 1. The degree of the denominator is 3. So the degree in the numerator is smaller than the degree in the denominator. Whenever you have an example like that, you have a horizontal asymptote where y is equal to 0. It's the x-axis. And the graph will approach that line, but it will not touch it. Okay, another scenario we looked at was when the degree of the numerator was equal to the degree of the denominator. So for example, if we had 2x squared plus 4 over x squared minus 3. Actually, let's go plus 3. Okay, notice that the lead term in each polynomial, in the numerator and denominator, both have a degree of 2. So the numerator has a degree 2, the denominator has a degree of 2. You would take a look at the first term, and the leading coefficient is 2 over 1, which makes your horizontal asymptote y equals 2 over 1, or just y equals 2. Okay, so your horizontal asymptote, whenever the degrees are the same in the numerator and denominator, will always be the leading coefficients of the term that has the highest exponent. Okay, and the very last scenario was when the degree of the numerator is greater than the degree of the denominator. So for example, if we had x squared plus 2x plus 7 over x minus 3. Degree of the numerator is 2. Degree of the denominator is 1. So that means the degree of the numerator is greater, and whenever that's the case, you will have no horizontal asymptote. So that's pretty much review from lesson 3. Lesson 4, we introduced something called a point of discontinuity. And the only way that will happen is if you have factors that are in common in the numerator and denominator. So you'll have factors that can cancel each other out. So I'm just going to make up an example. Say we had, say x squared plus 6x plus 5 over x plus 1. First step tells us we need to factor the rational expression. Okay, so if we do that, we'll get x plus 1 times x plus 5 over x plus 1. Now that we've factored it, we see that we have a common factor in the numerator and denominator. But we have to remember, before we cancel out, there is a discontinuity because we can't divide by 0. We know there will be a restriction at x cannot equal -1. Now, if there weren't common factors, we would say this is our vertical asymptote, x equals -1. But because we have common factors, we need to cancel them out, and we're gonna have a point of discontinuity that occurs when x equals -1.
Why is it -1 instead of positive 1?
If we put a -1 into this factor, it would make this entire binomial equal to 0, and we can't divide by 0.
But why would that cancel at the top one?
X plus 1 is the same as x plus 1. That's why they're canceling out.
So is the point of discontinuity, like, is that 1 or -1?
It will be at -1.
Okay, I'm just confused about like how would -1 cancel a positive 1?
Maybe let's start from the top. Okay, so when we factored, hi Hannah, we get x plus 1 times x plus 5 over x plus 1. Let's just rewind one more step. Let's look right here. What would be the restriction on the denominator?
X can't equal -1.
So x can equal -1, right? We know that's our MPV. So we know that there's going to be a break in the graph somewhere because x cannot equal -1. And then we factor it down here and we realize, oh, we have two factors that are alike. But we can't just cancel them out and ignore that there is a discontinuity. So although they're the same, so we can cancel them out, we have to remember there was an MPV because of the denominator, non-permissible value. When you have factors cancel out, it's not just a vertical asymptote anymore, it's a point of discontinuity. And that means there's a hole in the graph. Because what did we simplify to? This graph reduced to just a line, x plus 5. And so on that line, if I were to just draw it, we would have to have a hole in that when x is at -1. So the whole process here is we've got to figure out what is the ordered pair of that point of discontinuity. Right now we know x is -1. We've got to figure out what is the y-coordinate. So step 1, factor the rational expression. So we went from here to here. Step 2, we simplify by canceling out the common factors. And step 3, we've got to substitute the non-permissible value, which was -1, into the simplified form. Okay, so if we rewrite it, it's pretty much like y equals x plus 5. We're going to sub in, for x, that -1. Once we sub that in, we will then have the y value of that point of discontinuity. Y equals 4. So if I replace the y here, the hole in the graph is at -1, 4. And just a reminder with points of discontinuity, like if you were to graph this, it would come up as a line, but it wouldn't show the hole unless you pressed zoom decimal. Okay, so if you want to actually see the hole in the graph, press zoom decimal. Okay, moving on, we're going to look at an example of a function that has no discontinuities. Okay, so it's just going to be a continuous graph. We're looking at 1 over x squared plus 1. Without graphing this, let's see if we can answer this together. Does the function have any non-permissible values? So those come from the denominator. Is there any value of x that we could sub in so that the denominator would equal 0? If you put a -1 in there, it becomes positive, right? So you get +1 plus +1, not 0. What if you put a 0 in there? 0 plus 1 is still 1. Okay, you can never get a 0 in the denominator, which means that there's no non-permissible value. There's no NPV. So if we have no restrictions on the denominator or on x, because x can be anything, what will the domain be? Everything. Good. I'm loving the like charades game you're playing back there. Okay, part C, the maximum value of the function will occur when the denominator has its lowest value. So how can I make the x squared plus 1 be its lowest possible value? What would you sub in for x? 0, perfect. Okay, so if we put 1 over 0 squared plus 1, that gives us 1. Maybe I'll write f of x equals that. So the maximum value occurs at y equals 1. We briefly talked about this already, but part D is asking why the function can never be negative. We have 1 over x squared plus 1. So that numerator, it's always going to be positive 1. Can the denominator ever be negative? Why?
Because I'm squared. One squared negative, and it's supposed to be positive.
Perfect. So anything squared will be positive. So no matter what value of x, when squared, it will be positive. So any value that you sub in for x, when you square it, it's going to be positive. Part E, does the function have any zeros? Does it have any x-intercepts? How can I decide? Need a little help? You can't actually factor the bottom because it's not a difference of squares, it's just x squared, this one. So we can't factor it. Will we have any x-intercepts? Okay, let's talk about this. No matter what value of x when squared, it will be positive. Okay, will this ever be when y equals 0? Let's also talk about horizontal asymptotes. Okay, what's the degree of the numerator? 0. The degree of the denominator is 2. In other words, my question is the degree of the numerator less than the degree of the denominator? Yes, and if you have to, flip back. What's the rule? Okay, what kind of horizontal asymptote when the degree of the numerator is bigger than the degree of the denominator?
0.
Good. Okay, you have a horizontal asymptote at y equals 0. Therefore, no x-intercepts. Because this graph is never going to touch the x-axis. There's a horizontal asymptote, so it will approach the x-axis, but it will not touch it. Okay, so what's your maximum value? 1. Okay, and will the graph ever touch the x-axis? No, so we have a horizontal asymptote here. We don't have a vertical asymptote, but we have a max at 1. Okay, and let's just think about this. If I put in a -1, okay, -1 squared gives me 1, so I have 1 over 2. What if I put in a +1? What would I get? 1 over 2. Okay, so it would become the same. So no matter what I put in for x, whether it's positive or negative, it's going to be symmetrical. And if you guys need a little help, you can graph the function, this over this, in your y equals, but you'll get this little picture here. Okay? So just to review graphing, you want to make sure that you have proper window settings. So let's go 1 divided by x squared plus 1. Graph that. Okay, I have a wee little graph. Maybe I can make it better. So I'm going to change my window settings to -5 to 5. Actually, did they tell us window settings at the bottom?
Yeah.
Oh, what'd they tell us?
-771 for the x,
Alright,
and then -1 to 1.
okay, so -7 to 7, and then -1
-1 to 2.
to 2. Perfect, now we're gonna get a better picture. So, I know we probably could have figured out part F before graphing it, but I just want to summarize it with a picture. So, we all agreed that the maximum point is 1, and we have a horizontal asymptote on the x-axis. So, if this is the top value, and we're approaching 0, but we're not actually touching 0, what's your range? Y goes from where to where?
You're not.
Yeah, and the one thing we have to be careful about is it's less than or equal to 1, but it's greater than 0. Okay, it doesn't actually touch 0. So, in summary, would you guys say we have vertical asymptotes? Was there a restriction on the domain? No. Okay, so no vertical asymptote. Do we have any holes in the graph? No, no factors canceled out. Do we have a horizontal asymptote? Yes, it's at the x-axis, y equals 0. Okay, right here. Horizontal asymptote, y equals 0. So just flipping to the next page, we have a few graphs that we can explore. The first one we just talked all about, 1 over x squared plus 1. So we don't really need to discuss that one again. Just looking at part A, they want us to figure out what the horizontal asymptotes are. So just by looking at this graph, does it look like there's a horizontal asymptote? Where is this approaching? The x-axis. Where's this approaching? The x-axis. But we have this unique point. Okay, this is a tricky one. Let's take a look at our rules. Degree of numerator is smaller than degree of denominator. Therefore, we have a horizontal asymptote at y equals 0. This is a really unique case. Although we have a unique point crossing through the x-axis, everywhere else on the graph is approaching the x-axis or the horizontal asymptote y equals 0. Okay, so this does have a horizontal asymptote, it just has a unique point that crosses through. Okay, so you're just going to have to accept it. I know you want to fight it. I don't like it either. It's breaking all the rules. But the trend of the graph, as x increases, as x is going to infinity, it is approaching that line. And as x goes to negative infinity, it's also approaching y equals 0. So we have a horizontal asymptote, whether you like this point or not. Okay, let's look at the third graph. We have x squared over x squared plus 1. Does it look like the graph is approaching a certain line? Y equals 1. Good. And if we just remember our rules about the horizontal asymptote, if the degree is the same in the numerator as denominator, then we have to look at the coefficients in front of the leading term. And it's 1 over 1, which is y equals 1. So our horizontal asymptote is at y equals 1. If you guys want, just for complete notes, you could put horizontal asymptote here is at y equals 0. We've already talked about this graph, but just in case. And we always show dashed lines for those asymptotes. Alright, last one. We have x cubed over x squared plus 1. Degree is bigger in the numerator than the denominator. Do I have a horizontal asymptote? No, and from the graph I can see that because as x is increasing, y is going to positive infinity. As x is decreasing, we're going to negative infinity. There's no restriction there, so no horizontal asymptote. No ha. No ha. Per B, do the equations in A agree with the rules for the horizontal asymptotes for the reviews that we talked about? Is there one that's driving you mad? Yeah, 2. You will notice anytime you have a graph of x over x squared, you will likely have a line that crosses through the x-axis, but the general trend of the rest of the graph will be approaching that horizontal asymptote y equals 0. So, you just gotta breathe, accept it, and move forward. Okay, in this case, to find the range, you would have to locate the max and the min to figure out where it's going between. Okay, so you could use your calculator to do that. Okay, we've already talked about C, and part D we'll just discuss. So it's asking when we have x squared over x squared plus 1, why will it always be positive? And we pretty much talked about it from this example. Anytime you square an x value, it will be positive. So moving on. This next page I feel is very redundant. It's giving you a lot of examples, which is good, but it's I think stuff that you could probably do on your own in the homework assignment. Okay, and pretty much it's a review of what we looked at in lesson 3, 4, and what we've already talked about. You're discovering where there's discontinuities, so horizontal, vertical asymptotes, as well as if there's points of discontinuities. So rather than doing all of them, let's just go through one in detail. Okay, so algebraically determine the equations of any asymptotes and the coordinates of any points of discontinuity on the function given, and then we have to state the domain and range. Okay, let's start with points of discontinuity. What is the first step when you're finding a point of discontinuity? Very good, refactor. Okay, so right now we have f of x equals, they already factored the top for us, 2x minus 1 times x minus 5 all over. Factor in the denominator, I get x minus 5 and x plus 3. Let's just talk about our restrictions. X can't equal positive 5 and x can't equal negative 3. Where will the point of discontinuity occur though? And that's because it's the factor that will cancel out. Okay, so because this cancels out, our point of discontinuity occurs at x equals positive 5. So the factor that cancels out is where your point of discontinuity will be, where your hole is.
There's the opposite, right?
Pardon?
Opposite though?
These were the same, x minus 5 and x minus 5, so they canceled out.
Positive 5?
Yeah, whatever value of x will make that entire binomial equal to 0, that's what it will be. It's same with like when you're finding x-intercepts. Okay? So then we need to simplify this. So f of x now equals 2x minus 1 over x plus 3. So if the point of discontinuity occurs at x equals 5, how am I going to figure out the y coordinate? Good. I'm going to replace the x's in the simplified function, or expression. So these x's are going to be replaced with this 5. Okay, I'm just going to write that over here. So solving for y, we've got to replace the x with 5. And solve. And I get 9 over 8. So x equals 5, y equals 9 over 8. So if I wrote that as an ordered pair, my point of discontinuity occurs at 5 and 9 over 8. So if I were to ask you right now, just based on what we found from the point of discontinuity. If I asked you the domain, what would be one restriction in the domain? X can equal 5. Good. Okay, what about the range? Y can equal 9/8. Awesome, so we found our point of discontinuity. Now let's talk about our vertical and horizontal asymptotes. So vertical asymptote, let's start there. So f of x was equal to 2x minus 1 times x minus 5 over x minus 5 times x plus 3. So keep in mind, from the x minus 5, because that canceled out, we had a point of discontinuity. So what will we have from the other factor, x plus 3? X can't equal -3. So if x can't equal -3, that will be the equation of our vertical asymptote, x equals -3. What did you say, sir? You did say that,
Yeah.
okay. I thought I heard that, but then I was like, did he say something different? So, just making sure.
I think I said that, I don't really know now.
Okay, so the factors that cancel out, that gives you information about the point of discontinuity. The factor in the denominator that remains, that's what will be your vertical asymptote. So we have a vertical asymptote, point of discontinuity, and now let's look at our horizontal asymptote. Okay, what's the degree of the numerator? 2? How'd you get that? Good, he expanded 2x times x. So if I did expand the numerator, I would get 2x squared minus 10x minus another 1x, so minus 11x, and plus 5. All over my denominator, x squared minus 2x minus 15. And as we're seeing, we have degree 2 in both the numerator and denominator. And I just need to take the leading coefficients, 2 over 1. So my horizontal asymptote will be 2. So from that, I have a few restrictions, few discontinuities. What will my domain be? What are the restrictions on my domain? What can x not equal from the denominators? 5 and -3. Good. So we say x can't equal 5, can't equal -3. Everything else is a real number. Okay, and the range. What are the values that y cannot equal? Okay, from our horizontal asymptote, y can't equal 2. And from our point of discontinuity, y can't equal 9/8. Everything else is real. And just remember, you can always verify, check with your calculator if you want to plug that in, see what the graph looks like, see if you have any breaks in the graph that line up with what you've established here. Feeling good?